Okay, so probability, if you don't remember from algebra, is a number from 0 to 1, usually in decimal form, and it basically represents the decimal form of percentage. Okay, so if you have a probability of 0, that means that there's absolutely no likelihood it'll happen. A probability of 1 means it will happen every time. Okay, so it's 100% for 1, 0% for 0. And when you're calculating probability, you're always going to calculate probability as whatever the desired outcome is divided by all possible outcomes. And that's going to start to appear in problems that you have involving areas. Okay, so the way that it'll often be set up is it'll ask you, given this figure, what's the probability of a randomly selected point being contained in the shaded region or the unshaded region? Okay, so the way that you find the desired outcome, it's just going to be the area of the designated region that it's looking for, divided by all possible outcomes means the total area possible, unshaded and shaded combined. Okay, so that would be the second area scenario. Okay, and so if we looked at, this is sample problem 11, it's also on page 78. I'm going to kind of talk through this one. I have another problem on the next slide that you guys can do or try on your own. Okay, but let's talk through how this would be set up. Okay, if you wanted to find the probability of randomly selecting a point, having it be contained in the shaded region, we're looking at the shaded is our desired outcome, and it's over or divided by all possible regions, which is the shaded and unshaded combined. Okay, so when you look at this figure right here, just in terms of M and R, the shaded region is calculated using what equation? It's a sector, so it's M over 360 times pi r squared. And that's divided by the total region, which is the shaded and unshaded combined, is going to be what? Yeah, it's just the whole thing, right? So the whole circle has an area formula of pi r squared. So again, you can think of it 360 over 360, or just the pi r squared itself. So that's a whole possible, shaded and unshaded combined. So if you look to reduce this, did it even matter what the radius was for this? No, because you're going to see the pi r squareds cancel. You're left with m over 360. So if m is 45, and we simplify this, 1 over 8, and we find the decimal form for this, 1 divided by 8 is 0.125. And so what would this be? So here's the probability. Okay, so the probability is going to be that decimal value. If I had asked you to answer the question in terms of what % chance would there be of randomly selecting a point in that shaded region, the answer would be 12.5%. Okay, so again, make sure that you're careful, you identify what the form is that they're asking for. Okay. So what I want you to do, you can work with another person. Okay, see if you can figure out this problem. All right. So let's take a look at how we could set this up calculation-wise. So our probability is, make sure you read carefully, because one of the distinctions between like sample problems or the practice problems versus the actual quiz or test problems is I might change what I'm asking for. So it might be shaded region, it might be unshaded region. So here it's our shaded region is our desired outcome, and we're going to divide by all possible outcomes. Shaded and unshaded combined is simply the total area. And so let's see, how would we find the shaded region? Well, to find the shaded region here, we take the area of this large circle. Okay, let's call that a radius of r. So our large circle would be pi r squared. And from that, we're going to subtract all the small circles. So we have 5 of these smaller circles, 5 times pi. And let's call the radius of the smaller circles something else. We'll call it x. So 5 pi x squared. Okay, so there's the calculation for finding the shaded region. And we're going to divide that by the total area of the whole thing. Shaded and unshaded combined is just the area of this big circle, right? So that's represented by pi r squared. Okay, so here's our calculation. Now, we want to make sure that we can't have two different variables. So you have a couple choices here. You could plug numbers in. Okay? So you could let x just be a 1 or a 2 or whatever, and then find what the corresponding r would be. I'm going to go ahead and just leave it in terms of the variable. So if we build from the smallest variable, x, what is radius in terms of x? 1, 2, 3, it's 4 of those x's. Okay, so let's go back in and let's substitute all the r's for its equivalent 4x. So we have pi times 4x squared minus 5 pi x squared, and that's all over pi times 4x squared. Okay. Now, we still have these grouping symbols, so using order of operations, we need to get rid of those. So we're going to square the 4 and square the x. So we get 16 pi x squared minus 5 pi x squared in the numerator. In the denominator, again, 4 and x both get squared. We get 16 pi x squared. Can I cancel these x squareds in the pi here? Be careful, that's a common mistake that students make. Remember, I'm combining like terms here, so I have to combine my terms before I cancel factors. Okay, so if I combine my like terms here, I get 11 pi x squared over 16 pi x squared. And then I can cancel. My pi's cancel, x squareds cancel, and so I get my answer 11 over 16. So if I convert that into a decimal form, I get my solution 0.6875. And that is my probability of randomly selecting a point that's in the shaded region. Okay, which means what would be the percent chance of picking a point in the shaded? Again, the percent equivalent would be 68.75. Okay? So there's an easier way to approach this, but in order to use the easier method, you have to have an understanding of what I just talked about involving ratio of parts and ratio of areas. And so try to follow along. If you understand what I'm saying, it'll make some of the problems that you may come across much easier to solve. All right, so we know that this is the shaded versus the overall or total, right? All right, so let's think about this in terms of the ratio of parts. What's the ratio of parts between the small circles and the larger circles? The small one, for every one dimension on the single dimensions, every one for the radius of the small one, the larger circle is how many? It's 4 of them, right? So it's a ratio of 1 to 4. What does that mean the ratio of their areas then would need to be? 1 squared to 4 squared. So 1 to 16. So what that means is each one of these smaller circles represents what fraction of the bigger circle? 1/16 of it, right? And then how many small ones are there? 5/16 or 5, right? So the small circles represent 5/16 of the whole thing. And so if you remove those, if you remove 5/16 from the total 16/16, what's left? 11/16. And that would be your answer.